Hello dear students. In today's class, we will continue our discussions on ionosphere. So far we have seen what is ionosphere, how many different layers exist in ionosphere, what is the reason for naming all these regions as different layers but not a continuum of ionosphere. So these layers are preliminary D, E, F1 and F2. We have also seen that some of these layers will disappear during the night time due to the lack of direct sunlight or due to the lack of resulting ionization, right. So what we will learn today is an extension to the same discussion. So we have seen from the earlier class that if you look at the density of ionosphere, it will look something like this, right. So on the x-axis you have the number density, let's say the electron density on the x-axis, and on the y-axis you have the height. Okay. So here the basic idea was, we have seen that the peak which occurs nearly at 250 kilometers or 250 kilometers, we will see that the electron density peaks to nearly 10 to the power of 12 per meter cube. It is 10 to the power of 12 electrons per meter cube. So per unit volume there are 10 to the power of 12 electrons. So we also take it always that the number of electrons is always equal to the number of ions, so that the neutrality is maintained in the ionosphere. So at the peak, so the peak ionospheric density, always remember this number 10 to the power of 12 per meter cube. So if you calculate the plasma frequency, omega p is 9 times square root of Ne, which is 9 times 10 to the power of 6 hertz. So plasma frequency is a very large frequency for this peak ionospheric density. We know that this happens because the plasma frequency depends heavily on the mass of electron. So this is m epsilon naught. So where n is the number density, m is generally the electron plasma frequency we are calculating, the mass of electrons, which is 9.11 10 to the power of minus 31 kg. So what are we trying to do here? We are trying to find out, we are trying to realize what exactly is the ionosphere, right. Now from this simple discussion, one thing is evident. It is evident that electron density is not the same throughout the ionosphere. Electron density peaks at a particular value of nearly 250 kilometers at 10 to the power of 12 per meter cube. So if you evaluate the plasma frequency at this, it will be 9 megahertz. Fine. Right. In today's discussion, what we are going to do, what we will try to understand is that what is the reason that the ionosphere density peaks at a particular point. Before that it is less, and after that it is again less. Let's say we concentrate on this height. Let's say we concentrate on this height. So this is the height that we are trying to understand, let's say on this region. Okay, what do you see? You see that the electron density is increasing and then the electron density decreases. If you look up, electron density is increasing as you go like this, and the electron density again decreases, right. So why does such a thing happen? So this shape is generally known as the Chapman layer. So this Chapman's, we call it as the Chapman's layer. We have also mentioned at some point that this is the entire structure of the ionosphere. We have also mentioned that this structure of ionosphere is going to be split into 4 layers actually, D, E, F1 and F2. What was the basis for defining these layers is that whenever you see a turning point, this is the turning point where the slope changes its direction, right. This is the turning point. This is the turning point, right. So these are the inflection points where you have identified the layer. So everything below this you have called one layer, everything below this you have called another layer, and everything like that, right. So the point is, why do such layered ionospheric densities are seen in the atmosphere? That's going to be the topic of discussion for today. So this entire mathematical framework that we are going to derive is based on the Chapman's theory. So this is going to be the Chapman's theory. So, we will try to understand the layer production. So, for example, intuitively we can understand why does the electron density reaches a maximum, thereafter the electron density decreases, right. So, why does such thing happen, right. Now, from your basic understanding of the atmosphere, we have in the very beginning itself, we have made a remark saying that the number density of let us say neutral species, it will vary exponentially as you travel up. So, this is how it looks like. What is n? N is the number of atoms / molecules per unit volume, which is also in accordance with the pressure exponential minus h by h, or the density exponential minus h by h. Right. What it tells you is that if you consider a parameter which is called as scale height, which is kT by mg, this is a length dimension parameter, what you will realize is that as you go up, the density of neutral species will decrease exponentially, will decrease like this, will decrease exponentially. So, as you go up with the height, and you have the, let us say, the number density or the pressure or the density. Number of atoms or molecules that you can find per unit volume will decrease exponentially, right. Then this is something that we have known from the basic atmosphere or atmospheric thermodynamics for that matter, right. Now, if you plot, let us say if you have let us say with height, so this is n is equals to n naught exponential minus h by h, where h is the height at which you want to calculate the number density, capital H is the scale height, n naught is the number density at h is equals to 0. Simple, right. Now, if you simply look at how the radiation changes with respect to height, you have learned from the simple D'Alembert's simple rule that I is equals to I naught e to the power of minus mu tau, right. So, this is the idea of basic optical depth. You will realize that the density or the available photons at the top of the atmosphere will be very, very large, and as it travels towards the ground, the available number of photons will decrease. Why do they decrease? Because the photons will be consumed by the atoms and molecules which are existing in the upper atmosphere for the processes of dissociation or ionization. That means, eventually the energy that is available at a particular height, at the maximum height, let us say, is maximum. I mean, there are at the top of the atmosphere, let us say we consider the top of the atmosphere to be let us say 840 kilometers, for example. You take the top of the atmosphere to be 840 kilometers, where there is absolutely nothing, which is a near or perfect vacuum that is existing there. That means there are no atoms and molecules. Even if there are atoms and molecules, the typical mean free paths of these atoms and molecules will be several hundreds of kilometers. That means any one molecule will not come in contact with another atom or molecule for several hundreds of kilometers. So, that means there is, if you consider a cubical volume, there is, you think of the number of atoms that could exist in a cubical volume of, let us say, 1 meter cube. You will realize it is 0, right. So, what I am trying to say is, at these heights, when you consider what is the density of photons, or what is the amount of energy that is available to the Earth's atmosphere, which probably kind of enters into the Earth's atmosphere, is very high. As the radiation travels towards the surface, we have already seen that not all this radiation is relevant for the atmospheric species. Not all the spectral bands of this radiation are relevant for the atmospheric species. It is mainly the extreme ultraviolet and X-rays which will cause ionization and dissociation, thereby get consumed by the atmosphere. So, having said that, we can simply say that as the radiation travels towards the surface, more and more it encounters more and more amounts of gas species, thereby more ionization, more dissociation will happen. So, in this process, the photon density, the available energy that is coming from the top, gets consumed, right. So, as it travels. Now, so if you, the basic idea is to be able to combine these two. One tells you from the top the number densities are increasing at an exponential rate towards the surface, right, from the top, if you see from the top. And another tells you, if you say that it decreases exponentially, the number of available photons, energetic photons, will decrease exponentially as it travels towards the surface, right. Fine. Now, so now you can say that, see here the number of photons are maximum. You can say that we can get maximum ionization here, but it does not happen like that, because even though number of photons are large, there are not many atoms which could use these photons, right. So, as a result, when you combine these two plots, let us say, what you will see is that at some point the rate of ionization will increase drastically as the photons travel into the denser atmosphere, but there has to be a balance in the sense. So, as what you see from here is that this is now, let us say, the number of electrons / ions, because we are always going ahead with the assumption that the number of ions are always equal to the number of electrons, right. So, the point is, as the radiation travels towards the surface, it encounters more and more amounts of atoms or molecules, but at the same time the available number of photons are becoming less because of the absorption, right. So, these two things balance each other at a particular point. Let us say, let us call this point as H m. What is Hm? Hm is the height of peak production. So, this is where the energy that is available and the atoms that are available are balanced with each other. They are in balance. I mean, they are, whatever the amount of radiation that is coming out is appropriately or completely used by the atom. So, it is now at this point we can simply say that there are photons available. There are, let us say, there are 100 photons which are available, but there are only 80 atoms, right. 80 atoms which are completely, I mean, here the photon count is more than the number of atoms. So, 80 photons will get absorbed here, whatever the remaining 20 photons will travel downwards. Here, what was the situation? Let us say the same 100 photons available at the top, but there are only 2 atoms that are available. So, what will happen? So, there are 98 photons which are traveling downwards, right. So, here is the balance point where whatever the number of atoms that are available, they are completely ionized to let us say to an ideal case. That means here, even here, the photons are still outnumbering the number of atoms. It is not that you will never be able to create an atmosphere which will completely absorb whatever the photon count that is coming from the top. So, what happens now after this point, after this inflection point, when the photon count is, of course, most efficiently used, when the photons or when the energy travels further down, it will start encountering denser and denser atmosphere. That means now the photons are going to be little in comparison to the number of atoms. What happens? The production rate will decrease, right. So, now at this point there are 20 photons, but what happens after it travels? Let us say there are 1000 atoms. So, 20 photons will never be comparable to, let us say, 1000 atoms. What happens? As a result, the electron density or the production rate is the rate at which electrons or ions are generated, right. So, it will decrease. So, the point is, now due to a balance between the energy that is incident into the atmosphere and the density of the atmosphere, will strike at a point, and as a result you have something like this. So, this curve or this layer like phenomena is properly explained in terms of in mathematics by Sidney Chapman, right. So, what we will do is we will try to understand the mathematical framework. We will try to derive the rate at which the layer or the peak production happens, right. So, here our terminology will be mainly based on, let us say, two things. We will call Q as the rate of production and Qm as the peak production rate, and Hm is the height of peak production. Okay, so ionospheric layers. So this is going to be the topic of discussion for today. Now let's say, so how does the photons, how does the radiation gets absorbed? When radiation from the sun is absorbed in the atmosphere, it heats it. So the atmosphere is getting heated. So it heats it, it dissociates the molecule and liberates free electrons. The rate at which dissociation or ionization is produced, or which you can also call as the rate of production at any level, is proportional to the product of gas concentration and the intensity of radiation. So we can say that the rate at which production happens is proportional to the gas concentration. Let's say we call the gas concentration with N, gas concentration, and the available density, available intensity, right? Q is proportional to N and Q is also proportional to N. I is the intensity. So at the top of the atmosphere, the rate is very small because the concentration of the available species is very small. As the radiation penetrates downwards, the concentration increases, and with it, the rate of production also increases. Below a certain height, however, the strength of the radiation decreases downwards is greater than the rate of increase of the concentration. Thus, the height where the rate of production reaches a maximum is generally called as a peak of production, right? So the approximate level of the peak production can be deduced from simple arguments. Let's say we can use simple arguments. Let's say, suppose that the atmosphere consists of molecules all having the same absorption cross section. That means, so let's consider atmosphere made up of many different types of gas species, of which let's say we consider that all of them have the same absorption cross section. Sigma is absorption cross section. What are the units? The units are area. So what I am trying to do is, let's say we have oxygen, we have nitrogen, we have argon, we have carbon dioxide, we have so many other species, right? So in order to do this, the first assumption that we are going to make is that, see, these molecules or the atoms are of different sizes. So the rate at which a photon can be absorbed by these species will be different, obviously. Why is it basically different? Because these are of different sizes and the interaction happens as a function of the distance or the size of the atom or molecule. So what we are doing is we are going to say that sigma is the rate of production, sigma is the cross section, which is going to be assumed to be the same for all the atoms. And the radiation falls from the outside, possibly in an oblique direction. Now let's say we consider the earth like this and we consider the atmosphere like this, and the radiation is falling like this. Okay, so let's say this is the sun. So if the sun is in the noon position, the angle at this point, let's say we take it to be chi is equal to 0. At any other position away from the noon, the angle that is subtended by the sun is chi. What is chi? Chi is the solar zenith angle. Right. So what am I trying to do? I am trying to put the atmosphere like this in a column of let's say this, and we are saying that sun is at a point and it is making the radiation fall obliquely towards the earth, right? So why am I doing this? If the radiation falls normally, the height or the length over which radiation penetrates or travels through the atmosphere will be smaller when the radiation will be smaller in comparison to when the radiation falls in an oblique direction. Simple, right? So then in a column of unit cross section, let's say you consider this column of unit cross section, so the area is 1, then drawn in the direction of the length sufficient to contain n molecules. So what we are going to do is we consider this, we consider, let's say the radiation is falling like this, we consider a column of air like this, which is in this oblique direction at an angle chi. Let us imagine there are n atoms or molecules, let's say molecules inside, each of which have the same cross section sigma. Okay, so the total projected absorption cross section, what happens? The total projected absorption cross section for this incoming radiation. What does this radiation see? within a unit surface area, unit cross section, the total area this radiation is offered to ionize or to do whatever it is, right, is n sigma, right. Now, is the total absorption cross section that is being offered is n sigma. Now, how far does this radiation travel inside is the real question. The radiation thus descends to a level where the total number of molecules in oblique column or unit area is exactly equal to 1, where n is equal to sigma inverse, right. So, this is number per unit area, right, or the radiation travels to that particular height where n sigma is equals to 1. This is the condition for the radiation. So, when the rate of production is plotted against the height, the resulting curve represents what we call as the production layer. We have already seen how the production layer will look like. So, this is how it looks like, right. So, its shape depends jointly on the nature of, let us say, nature of gas, the angle at which the radiation is, the angle or the time during which you plot it. Time is an indirect function of the angle, right. So, let us say in the noon, let us say the sun is exactly on your head, so the angle is 0. So, the radiation is penetrating. How is it? How does it matter? Let us say this is chi is equal to 0, and let us say, so if you take the atmosphere like to be like this, if you have the sun rays directly, so this is chi is equal to 0, or we call it as noon, and let us say this is chi is equal to 45, whatever it is, the time, right. Now, what I am trying to say is, as the radiation travels, there will be a balance point where the production is maximum, right. Now, what you will realize is that as the radiation is traveling normally, it is taking less distance to reach the surface. If it travels oblique, in oblique direction, it will be traveling more distance, right. Now, as a result, because this is traveling more distance, the height or the penetration of the maximum energy will be to lower altitudes. As the radiation has to travel larger distances, obviously the penetration will be in the higher altitudes. That is the difference, right. So, it is thus convenient to establish the form of production layer when ionizing radiation falls normally or obliquely on a horizontal stratified gas distributed vertically with a constant scale height and having absorption cross section independent of wavelength. So, we are not considering the entire spectrum of, let us say, wavelengths, let us say 1 to, let us say, whatever 10,000 nanometers, for example, 0.01. So, the entire spectrum of sun, we are not going to consider this. This wavelength variation is not going to affect in any way the sigma. Okay, that is what we have taken, and we have taken all the species to be of the same cross section area, right. And we also say that the atmosphere is horizontally stratified. That means there are no variations as long as you are in one particular height. So, this is the basic framework before we start deriving the mathematics of the Chapman's theory of layer production, right. So, let us say we will go there. So, the topic is Chapman's theory of layer production. Who did this? Sidney Chapman. So, this is considered a very important or very key concept in understanding ionosphere, because various other parameters are to be included in this discussion. The research that happens in ionosphere in terms of the frequencies or in terms of the number densities, any fluctuations that you see always require a prior knowledge of Chapman's theory, because otherwise we will not be able to understand or we will not be able to appreciate any result as such, right. So, Sidney Chapman proposed this particular theory to understand how an ionospheric layer will form. What is the basic reason behind it? So, this ionospheric layer is typically consisting of electrons and ions. So, this theory was based on the fact that the solar radiation ionizes gaseous atoms and molecules which are present in the atmosphere. That's what we've been telling all the while. So ionization of atmospheric constituent depends on the intensity and the wavelength and the number density of atmospheric species. So ionization happens means, so ionization has to depend on the available number of atoms or molecules, the wavelength which is entering into the atmosphere, or what kind of atoms are there, right, all these things. So before we start the discussion, there are a few assumptions based on which the Chapman's theory of layer production was kind of derived. So we say that only one type of gas is present in the atmosphere, is present in the atmosphere. That means we will take that all the gases have a single cross section, right. The second assumption, the atmosphere is horizontally stratified. The atmosphere is horizontally stratified. What does it mean? There are no fluctuations as long as you are confined to one particular height. Things change only when you move up. Okay. The third assumption is the incident radiation is monochromatic and parallel. The incident radiation from the sun is assumed to be monochromatic. That means on a single wavelength, which is not like that. But for an assumption, we will say that the incident radiation is monochromatic and parallel. Okay. The fourth assumption is that we assume that the atmosphere is isothermal. The temperature is constant everywhere, so that we take a single scale height throughout. So scale height is Kh is equals to Kt by mg, right. So we are not taking any variations in g. That means throughout this height of, let us say, 250 kilometers or 400 kilometers, we do not say that g changes appreciably, we do not say that. And k of course is a constant, m is of course a constant because you have taken only one type of gas, you take the mean weight of the gas or whatever it is, but temperature, which is supposed to change as a function of height, is also assumed to be a constant because we can take a simple or single scale height for throughout the atmosphere. Otherwise, you have to substitute the temperature every single time when you change over a considerable altitude region. In order to avoid that, you take the same temperature throughout. Okay. Now, the idea of, let us say, solar zenith angle. So, we are just building up separate things for the Chapman's theory of layer production. We will add all of them together to derive the mathematics. Let's say. So, let's say this is the normal direction, and we say that the radiation is incident in this direction. So, this is the angle chi. So, this is the normal and this direction is incident direction from sun. Okay. So, this is the height dh, and let us say this is this height we refer as the oblique height as refer as dx. So, here chi is the solar zenith angle. Okay. So, we use simple trigonometry. Let us say we say that dh is equals to dx cos chi, or dx is dh secant chi. Let us call this relation as 1. Okay. So, when the solar radiation passes through the atmosphere, a fraction of intensity is absorbed and scattered by the atmosphere. Absorbed and scattered, right. So, let us say we stop here. We will take this mathematical treatment ahead in the next session. Okay. So, basically what we have learned is, we have learned how the number densities and the intensity of radiation from the top combine and give you a layer of ions or electrons, how these two things balance each other at a particular height, right. Now then we made some assumptions about how the atmosphere should be treated if you want to understand the Chapman's theory of layer production. So, okay. So, this is where we stop. We will continue this discussion in the next session. Okay.